So today I'm going to go through animation, AI, and also the input system if we have time, which I think we will. So animation. Let's start by looking a little bit at the goals of animation. What is it that we want to accomplish with the animation system? Well, typically with animation we have some parameter that we want to evaluate, and we have samples of this value at specific times. So we have a list of keys which consist of a timestamp and a value for the parameter at that time. This is not necessarily the only way you could do things. What we do when we do animations is that we take whatever we get from the animation program and we sample it at some fixed frequency and sample it out into timestamps and values like this. You could also try to represent sort of the actual data that you have in the animation program. Typically you have some curves in the animation program and so on. But we don't try to do that, because doing that, if you would try to replicate exactly what happens in the animation program, we'd sort of have to recreate all the structures that exist in the animation programs, whatever curves, whatever controllers, whatever stuff that the animation program has, we would have to have. And if we're supposed to support multiple different animation programs, that becomes really tricky. So we prefer to sample out the animation at some fixed frequency into just times and values, and then we go from there. So we assume that we have some sort of sample of the animation curve that looks like this. Typically we sample at 30 hertz, like 30 frames per second when we export, but we could sample at higher frequencies like 60 frames per second or something else if we need that for the animation. But whatever source data we start with in the DCC tool, we end up with exported data that looks something like this. And then we want to evaluate this data at some point in time t, which might not fall exactly on one of these timestamps that we have in the sample. It might be in between those, but then we can use sort of linear interpolation to find out the t value we want between these fixed keyframes that we have sampled. So it's the data that we want to represent, but we also have some other goals in addition to representing this sampled curve. The first one is memory use. We want to make sure that we keep that down. The reason is that animation data can grow big really quickly. If you consider a character rig, you can typically have 100 bones. In the character rig, you could have even more. And then you sample that at 30 frames per second. That means that you will have 3,000 samples for every second of animation. And for every sample, you have timestamp and some values. So you have a couple of bytes. Let's say that you have 20 bytes per sample. That's already 60K of data per second of animation. So if you start to have long-running animation, you quickly end up with megabytes and megabytes of data. So it's kind of important to keep the memory use down if we can, especially on more limited platforms. In addition to keeping the memory use down, we also are always interested in performance. So we want some kind of efficient playback of the animations. If you sort of try to do this in a naive manner, like look up the value at a time t given samples like this, a sort of naive implementation would do like a binary search to find the range where a particular time value falls in, and then do the interpolation in that range. But a binary search would be like O log n in the number of keys. And then we have to do that for every bone, for every animation. It quickly becomes quite expensive, so we want to avoid those binary searches. We also want to minimize what is called pointer chasing and cache misses, which is basically just reading from a lot of different parts of memory. So in modern computers, memory is often a lot slower than the CPU, unless you're hitting your caches. If you have to go out to sort of main storage, main memory, then memory reads are really expensive. They cost a lot of cycles. So we want to make sure that we, as much as possible, hit our caches whenever we read memory. And if we store our animation curves like this, like one curve per bone for this means that whenever we want to read the animation data for a particular bone, we'll have to go into a separate array for that particular bone, which means that we will almost certainly get a cache miss for every bone that we access. And if we have 100 bones that we need to sample for a specific time point, that means 100 cache misses, which is really expensive. And then we do that for multiple characters. It starts adding up to thousands and thousands of cache misses. And so it starts to become really, really expensive. So we want to find some way of representing the data so that we don't get those cache misses when trying to sample the animation curve. We also want to reduce the memory use. As I said before, we want to do that to conserve memory, but it's also good for performance, because the key to good performance when you're using memory is to hit your caches. And if you're using a lot of memory, you will fit less of your working memory in your caches. So reducing memory use also helps performance by allowing you to keep more data alive in the cache. Then another goal, which isn't as obvious, is streaming. This isn't actually, we don't actually use this right now for animation. I don't think we ever stream animation data right now in the engine, but it's something that you would want to support in an animation system. So suppose that you have a really, really long animation, like 30 minutes or something. You might not want to load that entire animation into memory at once. You might want to be able to stream that animation data in as you're playing the animation. This means that you can't sort of jump around in the animation, because then you will have to seek back and forth on disk to bring in the data. Instead, you want to consume the data linearly as you're playing the animation. It's the same thing as playing back a video file. If you want to be able to load each segment of the video file linearly, so you can start playing as soon as you get the first part of the video file and not have to wait for the end of it to appear. So if you do like a naive storage and store like curves like this for each bone, then we would have to jump around in the file in order to get to the last bone, for instance, would be at the end of the file. That means we couldn't stream the data efficiently. So we want to find a layout where we can consume the data linearly from beginning to end as we're playing the animation, and then it will work in a streaming scenario too. Notably, this is also good for performance, because if we're consuming data linearly, that's sort of the ideal situation for the cache, because then we can get good cache prediction of what memory we will use next, and we won't be running around all over memory. We'll just be walking it straight forward, which is the perfect situation for optimal cache performance. So these are kind of our goals to keep in mind when I start to talk how this is actually implemented. So I'll try to describe the animation system from like bottom up. So I'll start with the low level thing about how we represent animations in memory, and then I'll get into more like animation blending and animation state machines as kind of higher level concepts like that. So in the low level animation storage, we do a number of tricks in order to compress the memory use and in order to get this good cache behavior, this good linear cache behavior. So the first thing we do is to pack the data. So the data we have, these curves we have, typically they mostly consist of vector 3 and quaternion data, so positions and rotations. Actually mostly rotations, because Usually the position doesn't change that much, because usually in an animation your bones only rotate. It's rare that your bones actually stretch and become longer. So usually it's mostly rotation data. But this is the bulk of the data, and we want to compress that for lower memory use. So for quaternions, we compress them. So if you're familiar with quaternions, they have 4 components, so X, Y, Z, and W. But we actually don't need to store all the 4 components, because quaternions are normalized. So we know that the sum of squares here, I'm going to write it out, but the sum of squares is 1. And that means that if we have just 3 of these components, we can reconstruct the 4th one. So we only need to store 3 of the components. And we want, it's kind of nice to have a good even bits of numbers, like 16, 32, 64, because then we don't have to do bit shifting and stuff like that, which can take some extra time. So it makes sense to use 32 bits for the quaternion. So if we divide that by 3, that gives us 10 bits for each component to store 3 components, and we have some 2 extra bits over. So what we could do is we could store X, Y, Z with 10 bits each, and we know that they are in the range between -1 and 1, so we could use a fixed point representation within that range for these 3 components, and then we could just store 0 in the extra 2 bits that we have over for a 32-bit value. But we can actually do better than that by using these 2 bits. So what we do is that we use these 2 bits to identify the largest component in the quaternion. So we use this as an index. So we can use 2 bits to store a number between 0 and 3. So 0, 1, 2, 3. And that will indicate the largest component. So say that the largest component is Y here. Then we will store a 1 in these 2 bits. We know that Y is the largest component. And then we use these 10 bits per components to store the 3 other components except for the largest one, in this case Y. So why do we do that? Yes, I'll get to that. So the utility of this is that if we know that the Y is the largest component, then we know that sets a limit on how big these other components can be. Because if we know that Y is the largest component, we know that these are all smaller than Y. So the biggest X, Z, and W can be is if all 4 components are the same size. That gives us the maximum possible value for X, Z, and W, if Y is the largest one. So in this case, all components are the same size, which means that we have 4 times X squared equals 1. So, we know that 4 times X squared is less than 1, because otherwise X would be the largest component, and we know that it's not. Y is the largest component. So that means we know that X squared is less than 1 by 4, so we know that X is, I think I might miscalculate this. I think it should actually be the square root of 1, 2. Let's see. X is 4x squared. Well, I'm not gonna, I think it might be the square root of this instead. I'm not gonna try to figure this out while I'm talking. But anyway, it gives us a smaller range, because previously we only knew that x was in the range between -1 and 1. So we would use the 10 bits to store a fixed point value in this range. But now we have a smaller range for x. It has to be... Oh no! So I see now what I did wrong. The maximum value for x is if z and w are 0. So if x and y have the same value. So 2 times x squared must be less than 1. Because if 2 times x squared was bigger than 1, then x must be the biggest component. So x squared must be less than 1/2, and x must be less than the square root of 1/2 plus or minus. So x must be in this range, approximately. So this means that by storing the index to the largest component, instead of storing these 10 bits per component in the range -1 to 1, we can actually store these 10 bits, but instead use a fixed point range of -0.7 to 0.7, which means that we get better precision in storing these values. So we get some, because we have a smaller range here. So using the same number of bits to represent values in a smaller range means we get better precision. Which is really nice. And then we just reconstruct the largest component. So using this formula, we can reconstruct the square of the largest component. And actually, since quaternions, if you negate all the components of a quaternion, you have a quaternion that represents the same rotation. So we can just make sure that this largest value is always positive by negating all the components if it should happen to be negative. So we know that this one is always positive, and we know the square of it from the values of the other components, so then we can reconstruct this component. So that's the compression trick for storing the quaternions. For the positions, it's a bit simpler. We use just a 16-bit fixed point value in the range -10 meters to 10 meters, which is kind of the size that we expect our characters to have. We also support uncompressed values. If somehow these compression schemes doesn't give us high enough quality, or if the position is out of range, if we have a really big character that has positions outside the 10-meter range, we can't use these compressions. So in that case, we just default back to an uncompressed value. But these compressed values work for most cases. So that's how we compress the keys. Then we compress the curve itself. So instead of keeping keys and values for all these different keys, we reduce the number of keys we have. So we're trying to find a smaller representation of the same curve. We could do this by still using linear interpolation and just dropping some of these keys. But typically you get a better result by using some kind of higher order curve, like a secondary curve, a third-degree curve. Then you'll actually get, because animations tend to be smooth, so they tend to be curvy like this rather than jagged like this, which you would get if you use straight linear interpolation. So we use an interpolation polynomial called Hermite Curve. There is no strict need to use a Hermite Curve. It's not necessarily better than any other polynomial representation. You could use any way to represent third-degree polynomials like Bezier interpolation or other similar kinds of interpolation curves. The nice thing about Hermite curves, and the reason why we use them, is that with Hermite curves, all the parameters of the curves are values. So all the parameters of the curve. So if you use a regular third degree curve, you have something like a times t to 3 and b b times t squared, and so on. And then and then to store the curve, you store a, b, c, d. Now the problem here is, let me just write everything out. C times t plus d. Yeah, cubic Hermite splines, exactly. So the problem with if we use a representation like this is that, and this would say that this equates to a vector 3. The problem with this is that these things, this final parameter here, that has sort of the same dimensions as a vector 3, but these other things don't really have that. They are not necessarily in this range. They might be different kinds of values, and to compress them we would need a different kind of compression scheme. And that would kind of make things more complicated because, well, we found this nice compression scheme for the keys, but we don't really know what compression schemes we should use for these higher order curve parameters. And we would need to think about that and find out some other compression scheme, which is complicated. So the nice thing about Hermite interpolation is that the Hermite polynomial is written in such a way that these parameters a, b, and c and d that guide the Hermite polynomial actually are values. So they are actually vector 3s or quaternions, not some higher order thing, which means that we can use the same compression keys for these values as we don't need to figure out like special compression values for all these different parameters of the curve, which is really nice. We can just default to our standard encoding. So that's why we use the Hermite polynomials. And to build the Hermite curve from this sample data, we just start with a flat curve with just the endpoints, and then we measure the error tolerance, like how accurately are we representing these values of the original curve, and we have some threshold, how much error we're willing to accept. And if we have a bigger error, we'll add a new key in the middle of the original segment, and then we'll recurse and do this for each part. So we'll go into the first part of the Hermite curve, check the error we have in that part. If the error is still too big, we add a new curve point in the middle of that and continue like that. This is sort of a balance between like something that is fast enough, because it's not, you could like consider other schemes for building up this curve. You consider, should I add always the new curve point in the middle of this curve? Maybe I should add it more biased toward one end of the curve if I need more precision there, and so on. But that kind of becomes more expensive in order to find a good curve interpolation of the original data. So by just adding the midpoint is kind of a good compromise between something that runs reasonably fast, because we don't want compile times that take forever. So something that runs reasonably fast and still gets a pretty good interpolation with a small number of keys. But you could experiment with this with other ways of finding the curve and see if that can make you accurately represent the original curve with fewer keys. An important thing to note that can appear as a bug is that we are not able to represent animations that rotate really fast. So if you have an object that is spinning super fast, we can't really represent that. And the reason for that is this sampling that we do. We sample at some fixed frequency, and at that frequency we store the quaternion of the bones. And a quaternion of an object just represents an orientation of that object. It can't represent, it doesn't know if the object has like spun around multiple times to get to that orientation. There's no way of representing like multiple laps of rotation with a quaternion. It's just a single orientation. So if an object is rotating really fast, it might be that it completes a full rotation in the time it takes for us to take our next sample. So if the object does a full rotation or more than half a lap of rotation in our sample frequency time, then we won't actually see that rotation. We will see it as just a small rotation from the original position here to maybe this orientation here. Yeah, visually, well, it actually matters. I mean, if you would only ever see the sample points, it wouldn't matter. It would visually mean the same thing. But once you start interpolating, it doesn't mean the same thing, because if we have this sample point and this sample point, we will interpolate in between them like this. But if there was actually in the original data a full rotation between those 2 points, our interpolation should actually be like this. So the users will not get what they expect if they have something that rotates really fast. So if you need that, if you need super fast rotating objects, all you can do in our engine right now is actually to increase the sample rate. I mean, probably, I don't know if you really need an animation of an object that spins around at like 30, 60 rotations per second or something like that. But if you need that, you need to increase the sample rate. Another option, which we don't have in our engine, but that you could imagine, is to use some kind of different representation. Instead of using a quaternion for representation, you could use Euler angles. And Euler angles actually allow you to represent multiple laps of rotation if you allow the Euler angle to go beyond 360 degrees. You could say that the Euler angle is 10,000 degrees, and that would mean that it's actually spinned around like 30 times. But of course, Euler angles have other problems like gimbal lock and stuff like that, which is the reason why we don't really want to use them in our animation system. So, not a big deal, but this is something that can come up, and in some situations it's good to be aware that there are limitations to what we can represent. So, streaming, the streaming portion of it. So this part actually covers all the compression we do, compression of the keys and curve interpolation. So streaming is more about how we arrange the keys in memory. The most natural thing, as I said before, would be to just store the keys of one curve, one after another in memory. Like here's one curve, all its data, the next curve, all its data. But then we have this tricky problem that playback would require then from reading from all these different memory positions, like one curve here, the next curve here, the next curve over there, which is bad for performance and doesn't give us this streaming behavior. So what we do instead is to multiplex this data. So we take all the data from all the different bone and we sort it by time, so that instead of being sorted by bone first, all these keys are sorted by time first, which means that as we progress through time, we sort of progress linearly through the array of data. So we have for each curve sample, we have a data item that looks something like this. First, there's a type identifier using 2 bits. To your note there, Julian, we do linear interpolation of quaternions. There is some debate about whether that is actually the right thing to do or not. I think the conclusion sort of that debate is that linear interpolation is actually the right thing that you want to do rather than classical spherical interpolation of quaternions. But there are web pages to read on that, and I won't go into that debate. Anyway, since we use the linear interpolation, also when we sort of evaluate how well our interpolation is doing, when we measure the error tolerance, that kind of sorts itself out. Because if if there is any problem with the interpolation we use, that would show up as a high error tolerance, and then we would add more keys to sort of cover that error. So it kind of works itself out when we do the curve fit. Anyway, so we have keys that look like this in the multiplex data. So first, there are 2 bits that identify the type of the item, which can be either a compressed quaternion key, a compressed vector 3 key, or some other thing. We have 2 extra values here. Since we have 2 bits, we can represent 4 values. And those extra values are used for things like uncompressed data and stuff like that. But I'll only be talking about the compressed data since it's the most important case. Then we have a bone identifier, which identifies which curve these keys belong to. Since the keys are no longer sorted by curve, we need to know which curve each key belongs to. Then we have the time value. We use 20 bits for that, so it's sampled in some range here. Again, if it falls out of the range that we support, then we default to uncompressed values, so it will store more data, and I won't go through that format, but we can support values outside the range, but just not in the compressed format. And then we have the data itself, which is either 32 bits for a quaternion, as we saw, or 48 bits for a position, 16 bits for each component. So this is like each one of these keys get turned into an item like this, and then we put all these items in a big buffer sorted by time. Then to evaluate the curve, the Hermite evaluator, since it's a cubic polynomial, it needs 4 sample points in order to reconstruct the curve. So we have an evaluator that stores the current 4 keys that are used for evaluation. So it stores the 4 keys that we need to evaluate the current curve segment for the animation. And what happens when we advance time is that we read new data items like this, and we shift them into the evaluator for the bone that's specified here. So if we encounter a new key for this bone here, it will shift out this key, and we will have a new set of keys for the Hermite curve, which consists of these 3 keys and the new key that comes in here. And then we can continue evaluate. So advancing time, we just process this data linearly and add the keys that we find to the evaluator. And then when we need to evaluate the curve at a specific time, we just use these evaluator values that we've copied out of this data. So this is accessed locally and doesn't cause cache misses. We just evaluate the curve using these parameters. Now a little subtlety here, which can be important to be aware about, is that I said that keys are sorted by time. They are not actually sorted by the time value of the key here. They are sorted by the time when the evaluator needs them, so that we can process the data completely linearly and just add keys to the evaluator. So to understand the difference here, let's look at what happens at time 0. So time 0, when we start evaluating this curve, we need the first 4 keys. So we need the keys T1, T0, T1, T2, and T3, because we need 4 keys to form the polynomial. So all these keys are sorted with the sort value 0, because we need all these keys at time 0. At time 1, we don't need this segment anymore. We've passed through this segment. So at time 1, we will need these 3 keys, time 1, 2, 3, and a new key, time 4. So that 4th key is sorted at time 1, because that is when we need that key. So it's just a little subtlety to keep in mind, that the keys are not sorted at their actual time values, but at the time when they are needed. One consequence of our representation of the data here that is really important to be aware of is that we have no way of efficiently jumping in the animation. So we're depending on processing the keys in order in the stream. And it might be that, so we might have one curve that has very few keys. So one curve might have keys just at time 0, and then all the way here at time 60 seconds maybe. And then we have another curve that has a key at time 0, that might come after that in memory, and then it has a key of time 1 until time 2 until 3, and so on. So we don't know where in the sort of animation stream data where we will find these keys. So if we need to jump forward to time 60, we don't know where that key might be stored in the data for all these different bones. The only way we can get to a specific time point is by playing through the animation, walking over all this data until we get to that particular point in time. Also, we can't play animations backwards in an efficient way, because the keys are sorted by the point when they are needed for forward evaluation of the animation. If we're trying to play it backward, we don't know where to find the key. We know, so if we played this backward, then when we got to this segment T1 here, we would need to find T0, but it wouldn't be stored just before this key. It could be stored at any point before this key in the time. So we have no efficient way of jumping in animations and no efficient way of playing them backwards. On the other hand, we have an very efficient compressed format that streams well. So currently in the engine, if you want to play an animation backwards, you have to double the data. So you have to store both the forward animation and the same animation in backwards order, which is kind of annoying because there are a lot of situations where you want to play the same animation backwards and forwards, like a door opening and closing and stuff like that. So it is kind of a bit annoying. So this is maybe something that we want to fix in the future. It's not super clear how to fix it using the format of the data that we have. There are some different things you could do. We could introduce sort of synchronization frames. That's typically what you have in video encoding formats, like MP4 and stuff like that. Those formats are also limited to playing forward, but you have sync points like every, I don't know, 5 seconds or something, so where you store all the data that are needed at that point in time. So if you need to jump forward, you can jump to one of those sync points and then continue to play forward from that point. So that deals well with jumping. You can just introduce sync points as often as you need them and then jump to one of those and then continue playing from that point. But it doesn't really solve backwards playing, because to backward play you would still have to jump to the sync point before you and then play forward until the time just before you, and then jump back again and play forward and jump back again and play forward. So it would be more efficient than the only way we have of playing backwards today, which is jumping to the beginning of the animation and playing it all the way back up again to where you just were. But it's still not a very super efficient way of playing backwards. Another thing you could do maybe is introduce linked between paired keys, so that store some kind of offset in the key, so that this T1 stores an offset to the T0 key, so that we know where to look for that key when playing backwards. Something like that could maybe be done. Or we could try to rewrite the streaming format in such a way, in a more general way, to support sort of two-way streaming, playing backwards and forwards. So just some random ideas for how to support backwards play if we think that we need to do that. So that's how the sort of lowest level evaluation of animation works. We also multi-thread the animation using the job system. So we have a class which is called the animation player, and it keeps track of all running animations, and it creates a job for advancing the time for them, and then runs that job through the job manager. So let's see if we can find the code here. Let's look for set input ring. So yeah, this is the code that does that. It goes through all the current playing animations, sets up job data for them, like the current time of the animation, the stream data, active bones that are used, stuff like that, and sets up that input to a job, sets the kernel function, which is a function that moves through this data and interprets it and updates the evaluator, and then runs that as job to the job system, and then wait immediately afterwards. So it's one of these branch out, join together kind of multi-threading situations. One thing to note if you're looking at the animation system is that the header structure is a bit weird. The files are sort of broken up in more files that seems reasonable. We have one file, interleaved animation.h, which is used to represent this multiplexed format. It's called interleaved since the keys from different bones are interleaved. But then there's a file called interleaved animation job.h that has some of the same structure too, and it's sort of split up between these two files. The only reason for this sort of weird organization is that we used to support PS3, and the animation job used to run as an SPU job on the PS3, and SPU jobs are compiled as sort of separate executables from the main executable, and we don't want to compile all the engine code into the SPU job because SPUs has limited amount of memory, and that memory is shared for both the code for the job and the data. So we needed to sort of break out just as little as possible as was needed by the SPU job, and put those things in separate header files and separate CPP files. So that's why we have this kind of weird structures. Now we're not supporting PS3 anymore in the latest versions of the engine, so this structure doesn't really make sense anymore, and it should probably be refactored into something simpler, like moving these together into the same file again. But if you're confused about where to find things and think that it's weird that the same things are sort of divided into multiple files, yes, it is weird, and this is the reason for it. So we have another sort of optimization feature called animation merging. This optimization is used for things like army animations. If you have a huge number of characters that are all playing the same animation, like an army marching would be a typical example, and they all start at the same time and play at similar speed, we actually try to merge those animations to a single animation playback, so that we only have to evaluate the animation once, and then it can be reused by all these characters that are sort of walking in sync. And the animation player tries to do this automatically by finding if we find animations that are similar enough, it will try to merge them. And if for some reason they stop being similar, like one of them changes the speed or one of them jumps in time or something like that, then they will be split into separate evaluations again, instead of being sort of evaluated together. We also support general curve data in the animation, so it can contain data other than bone positions and bone rotations, just arbitrary float curves that could represent light values or something like that. You could ask why we have like these two, why we treat these things as separate things. Shouldn't we just treat the vector trees as float curves too, and the quaternions as float curves? That's pretty much what they are. And the only reason that we treat them differently is to do more efficient packing, because since we know that a quaternion has these special properties that it's normalized and so on, we know a good way of packing that data. If it was just a general curve and we didn't really know what it represented, we couldn't do that kind of efficient packing. So that's the only reason we have sort of different ways of representing the data. When compiling the data, the source data for animations comes from FBX files. So we use the FBX DLL to sort of load the FBX file and evaluate do the kind of sampling, evaluate the animation at specific points. We have a skeleton file that lists the bones in the character and the compression settings that should be used. Well, the compression settings are not in the skeleton file. I think they are in another file. Anyway, we have a file that specifies the compression settings that should be used for each bone. So you can sort of control the kind of, yeah, exactly. There's an animation clip file that stores the compression settings. So you can control for each bone what kind of compressions it should use. In the compiled animation data, we identify the bones by their index in the skeleton. So it's just an index reference for each bone. Typically, the way our animations will contain local space transforms. So, but by local space transforms, I mean that they contain the transform with respect to the parent node. So if I have my arm and my wrist, and it's like this, the wrist has the same rotation as the arm, it would be a 0 rotation, no matter where stored for the wrist, no matter where we were in word space. So there are two options for storing transforms. You could use local transforms, which is you store the transform relative to the parent node, or you could use word transforms. Say use word transforms, and the rotation of the wrist would change just by rotating the elbow, even though the wrist itself hasn't moved with respect to the elbow. The reason we use local space transforms for two reasons. First, they are typically better for compression because they typically have simpler movement. Like the wrist here, like when I'm rotating my arm like this, the wrist isn't moving at all in local space. So the wrist has a very simple flat curve. However, in world space, the wrist has this weird sort of rotation movement going on. So it's a much more complicated movement. So since movements in world space tend to have more complicated curves, if we represent them in local space, they will actually compress better. The second reason we're preferring local space transforms is that they're better for blending. As we will see later, we want to blend multiple animations on top of each other. So we might want to blend an aiming animation with a recoil animation like this. And by doing it in local space, it's kind of easier to understand what happens with blending. It's a bit weird, like if we try to blend in world space and the recoil animation, the aim animation switched the direction of the arm, and then we tried to apply this recoil thing in world space. I'm not sure how blending in world space would even work. To be honest, I haven't thought super much about it. Maybe there's things you can do, but I don't really know. So these are the reasons we use local space transforms. But using local transforms also have a big drawback. The drawback is that the error in the animation can be multiplied along the bone chains. So if you have a long bone chain, like your arm here, and I have a small error in how I represent the shoulder rotation, that error will translate to a pretty big error over here in where the hand ends up. So, and when we do the sort of curve sampling and try to get things below a certain error tolerance, we don't really know how the error will be magnified, because we don't really know what the character looks like and how long the bone chains are and how much error we will get here. So this leads to problems where we get like bigger errors like in the extremities than we might expect. And in a lot of cases, this is not super visible. Like, because if you have a jogging animation and you don't really care if your hand appears exactly here or a little bit like that, it doesn't really show. The situations where you can see this error multiplication is in foot sliding. So when the character is standing still, or when the character is running and the foot is in contact with the ground, in the animation you typically make the foot completely still at any moment that it's in contact with the ground, because you have friction there and the foot wouldn't normally move. But because of this error, you can sort of see the foot sliding around a bit, because even though the foot is completely still in the animation, the error that gets multiplied through the bone chain makes it move a little bit, and you can sort of see a weird movement like that on the foot. Another situation where you might see this is if you have some kind of like aim animation where you pull up a gun and put it right in your eye, and have a running, so you have some animation going on with the elbow, but the hand is supposed to be still with respect to the eye. Then you might get the error amplified through the elbow, and you might get the gun actually moving with respect to the eye, so it will bob around in the screen like this. So what can be done about this? Well, we could switch to using world space transform. I don't see how that will work, actually, mostly because of the blending. I think some people do it, but I'm not sure exactly what they do. But it would be interesting to find out. But instead, the typical things we do is we add constraints. So to stop the foot sliding, you would add a constraint that keeps the foot in contact with the ground, and keep it non-moving when it's in contact with the ground. I think Human IK has solutions for that too. And the same with the aim, you would add a constraint that actually locks the gun in place with respect to the eye, so that you don't get this bobbing. So that's typically the way you get around this. Another solution in some cases can be skeleton, sort of rethinking how you organize your skeleton. Now, a typical example of this that I've seen was an animation where you had a character fighting with a ball and chain. So it was animated so that the original setup of the skeleton was that you had a long bone chain going from the hand through the chain all the way down to the ball, and then the ball was lying on the ground, and the ball was supposed to be stationary while the chain moved around until the character sort of swinged, which would lift the ball up from the ground. Now, in this case, you would have a super long bone chain with this whole chain going down to the ball, and any sort of movement like this would make the ball move around on the ground like crazy. The solution was to change the linking, so to not link the ball actually through this bone chain, but to link the ball directly to the root position of the character. And that way you can sort of animate the ball without getting this chain effect from the chain. Essentially, it becomes kind of like you're animating the bone using world positions, because you're just linking the ball to the root. So you get that's kind of the solution, getting world position animation for a single object. we have, so that sort of covers the low-level animation. The higher-level animation system is concerned about blending multiple animations together. So for doing something interesting with a character, you typically want to blend different kinds of animations together in interesting ways. You might have a running animation, an aiming animation, a stopping animation. You want to be able to transition between these animations in a nice way, so to go from walking to running to stopping to jumping. And you also want to, for running, you maybe have animations for running in different directions, and you want to blend them together in interesting ways in order to run in a specific direction. You also may want to add animations on top of other animations, like adding a recoil animation on top of an aim, as I talked about, or adding like a hurt animation on top of the running animation, where the character is like a bit hurt when it's running, and so on. So this is the responsibility of the animation blender class. It allows multiple animations to blend and crossfade between them, so on. So there are multiple ways you can do blending. Some systems, some engines have like a completely customized blend graph, which means that you sort of set up how add these two animations, mix in this animation on top of it, subtract this animation, and you sort of construct a blending graph by hand for how the different animations should work together. We don't do that. We instead have sort of a fixed blend graph based on the typical kind of blends you want to perform. And I'll try to explain a bit what goes into this blend graph. The first feature of it is that it has layers. So you can have multiple layers of animations playing on a character, and you have separate animations playing in each layer. The higher layers will play over the layers below them. So if you have a character running in a low layer, and then you have a character sort of falling down in a higher layer, that falling down will take precedence and play over the running animation. But the higher layers, in the higher layers, you can also specify a per bone opacity, which means that when you specify that opacity, that controls how they override the animations below them. So if I could have a running animation like this, then I could have an aiming animation that is like this. And if I then add a blend, per bone opacity that says that the higher layer should only apply to the arms, then I get an animation where the character is running with the legs, and the shoulders may be jumping a bit from the running, but the arms are playing from the get their animation from the higher layer. So this allows you to sort of layer multiple animations on top of each other to sort of get this mixed effect. The other thing that's supported in the blend graph is crossfading. And crossfading happens when we transition between animations in one layer. So if you go from running to jumping in sort of the base layer, we do a crossfade over between the running animation into the jumping animation to get sort of a smooth blend between them. We also support mixing animations. Mixing animations means that we're playing a number of animations, and each animation has a certain strength that is the strength it should be mixed in with the other animations at. This is typically used for basic movement, where you have maybe a walking animation, a running animation, a turning animation, and then you play some mix on them of these animations depending on how fast the character is moving and how much the character is turning. You sort of control the blend values of that mix to get just the animation that you want. And these mix strengths are actually controlled by this expression language that I talked about in the math lecture. And then we also support constraints on top of this. constraints are actually callback functions that are applied to a pose after it has been computed from the animation. So if we have an aiming animation like this, we could apply a constraint to it that sort of redirects the aim to aim towards a specific target. So it can perform a general computation, whatever kind of general computation, in order to effect that pose. An interesting thing to note about the way our constraints work is that the constraints are applied to each individual animation before they sort of go into the blend graph and start blending with other animation. And so this is important for getting correct blends of these constraints. So if you have a running animation and it stops into and it transitions into an aiming animation which has a constraint like this, if we just apply the constraint full on, then it would be running like this, and then we would apply the constraint like this, and then so the constraint would apply immediately, and then we would blend over into sort of the aim animation and get the right thing, which wouldn't be the correct way of blending. The correct way would be to blend from the running animation to the aiming animation with the constraint applied, which is what we get by applying the constraint to the aiming animation before it enters into the blend system. So this is the most correct way to do constraints, but it's also kind of expensive, because if we have multiple animations doing the same, which have the same constraint, we need to apply the constraint individually to each of these animations before we blend them. So we might have to apply the constraint multiple times. And each time we apply like an aiming constraint, we need to go into world space to figure out where the character is actually aiming, and then go back to local space in order to get the bone positions for blending. So this is correct, but it can be kind of expensive. So one thing I've been thinking about is if we should also have kind of a simple constraint concept that is just applied at the end of all animations, like when we evaluated the complete animation state of the character, done all the blends, and that maybe we should have like a callback function that can apply a simpler constraint just on the world position of the character. So that's an idea I've been toying with, and I think it would be useful, but it's kind of tricky how to UI-wise sort of distinguish the simple constraint from the more complicated constraint, and how do you present to the user that there are two kinds of constraints and stuff like that. So, but I think it would be useful, but it's just kind of complicated how to present it. You start looking at the animation blender. There's quite a lot of math and quite a lot of making sure all the T's are crossed and I's are dotted to make sure that all of these different blends actually blend together in the way that you would expect, which is not always trivial in terms of how they are applied and in which order they are applied for the result to be correct. You could question, well, instead of you having this like fixed blend system, should we have a completely custom blend tree instead? Actually, I don't think so. I think if we did a custom blend tree, it would probably end up being something like this anyway, and at the same time it would be harder to control what's going on, because we wouldn't have this clear understanding of what these different things mean. We have a clear understanding of what the crossfade is, and we had a clear understanding of this layer concept. And if it was more general graph, the semantics wouldn't be known by the engine in the same way. So I'm not sure we would be able to control the blending as accurately as we do now. So I kind of like having this structure. What I would like to do to add a bit more flexibility is to be able to add sort of blend tree states into the sort of kind of animations that this thing can support. So in addition to having like regular animations and these sort of mix animations, there would be an extra thing which would be like a blend tree animation. And in a blend tree animation, you could do a complete custom blend tree of multiple animations and blend them together however you wanted. But it would still be a part of this sort of simpler system. You could do everything with the blend tree if that's really what you wanted, but for the people who don't want to do that, they would still have this basic system in place. I think that's where I would want to go with that in the future. Constraints, yeah, as I said, it's a callback function. They take a pose, return a modified pose. They have access to the scene graph so that they can apply the constraints in world space. But since everything needs to go back into the blender to be blended, they need to convert to world space to aim against a real object in world space, for instance. But then they need to convert everything back to local space so that the blender can blend it. So it's a bit of conversion back and forth that happens in these constraints, typically. One thing I should say about constraints in general is that I tend to prefer to have simple constraints rather than complicated solvers. Sometimes you see constraint solutions which are like, well, to solve the constraint, we solve these linear algebra equations. We set up a bunch of matrix linear algebra equations, and then we solve them to find the best solution, and so on. I tend to prefer simpler things where it's straightforward how the constraint is applied, like things like, well, take this bone, turn it 30% toward the target, take the next bone, turn it 50% toward the target direction, and then take this bone and turn it 100% toward the target direction. Something simple like that rather than solving an equation. And the reason I like that is because these constraints will be playing on top of a changing animation underneath them. And if the constraint is some complicated equation, it might transition from when the animation is in this state, it might find a solution like this, but maybe the next frame the animation is like this, and then the constraint will find a different solution like this to be optimal. So the result will be that the character will immediately pop from like this position to this position. And by using kind of simpler constraints it's very easy to see how the constraint gets applied. We can make sure that we don't get these sudden transitions in the solutions where a bone suddenly flips. There are probably ways of using more complicated equation solving constraints and still prevent this kind of popping by taking into account what the previous solution was and stuff like that. But I think these simpler approaches work really well, so I kind of prefer that. An example of a constraint we have in the engine is the aim constraint used for redirecting an aim animation towards a particular target. We have a loading system for the animations. So the reason for this is sometimes when a character is far away, you may not want to evaluate the animation for all its 100 bones. If the character just takes up like 10 pixels on the screen, you won't see that animation anyway, so it's kind of wasted effort. So the way we do that is that in our bone file, in our skeleton file, we sort the bones in order of importance. So we have the most important bones first, and then less and less visible bones, like things like fingers. And we do animation loading simply by only evaluating the first n bones, whatever that is, of the animation. So we can sort of adjust this. The character is really far away. Maybe we just evaluate the root bone, and if it gets a little bit closer, we evaluate the femur and the spine and stuff like that. If it gets really close, then we start evaluating the fingers. And when we do this, the rest of the bones, the ones that are not animated, will be frozen in their current pose, whatever that is. So the highest level above the blender is the state machine. So the state machine is sort of the connection between the animator, what the animator does in the editor, and the blender. So the state machine takes a state machine file that is created by the editor, and it's created by the animator by creating animation states in the editor and defining transitions between those states. And defining also events that cause transitions between these states. So the animator would draw a graph with different states, each state corresponding to one particular animation, drawing transitions between those states, and when an event occurred, a transition is taken and we move into that state. So the events here are just strings, and they are typically sent by the script. So the script will say, play the event jump, and then if there is a transition from the current state, which might be a running state, into the if there's a transition labeled jump with the jump event, the state machine will take that transition and go into the jumping state. So in the states we have things like playback speed, and they are controlled by variables and expression languages. So you can set the variable that is, say, the running speed, and then that running speed could, through an expression in the expression language, translate to a playback speed for the run animation. And we have states corresponding to the different kind of animations we have in the Blender. So we have a mix state that represents a mix of different animations, and so on. These transitions between the states that are triggered by events, they also have parameters. They have parameters like crossfade time, like how fast should we crossfade between the animation before and the animation we're transitioning into. They also have some synchronization features for when the transition should be taken. So one such synchronization feature is beat synchronization, and beats are like labels that you can create in the animation. So you could create an animation, you could create beats in animation specifying when the left foot is down and when the right foot is down. And then you can specify for a transition, a jump transition, for example, you can specify, well, this jump transition should be synchronized with the left foot is down. So the jump will actually wait until in the running animation the left foot hits the ground, and then the jump will sort of take off from there. So we'll get a really nice transition into the jump. So there's stuff like that in the specified in the transitions. And scroll down to animation state machine. Yeah, this is the class driving it, and you can send trigger events here, update for updating the state machine, controlling variables, setting targets for the constraints, like positions and rotations that constraints should try to achieve. So that's pretty much it here. Interesting to note too is that we have a sort of parent class that knows about all the animation state machines and can update them in parallel. So this again does an update through the job system where we go wide and update each state machine on a separate thread and then join the threads again. We also have triggers in the animation system, and those are events that occur at specific timestamps in the animation. They are just represented by ID strings, and we feed them from the animation player. So when we play the animation in the animation player, we notice when we encounter these triggers, and then they are fed up from the player up to the Blender and then up to the state machine. And in the state machine, they are sort of entered into a queue. So the state machine has a queue of all the triggers that has occurred. and this queue is polled by the world, which is the class where all the objects live. And the world will poll this queue and trigger flow events. I'll talk more about flow. It's our visual scripting language. I'll talk more about that in the future. But the world triggers flow events in the unit who owns the animation state machine. So this is kind of a typical setup how we do communication between different systems. So if you want to have a sound triggered when the foot hits the ground, you would create a trigger in the sound or in the animation for when the foot hits the ground, and then in the flow graph for the unit you would connect that trigger into playing that sound. So the sort of principles we have here is that we have no direct connection between the low-level systems, so the animation doesn't call directly into the sound system or something like that. Instead, all the communications is mediated by a higher-level system, in this case the world and flow. And this is to avoid tight coupling between different engine systems. And we want them to be as independent as possible, so we can do things. This is also things that allows us to multi-thread the animation state machine update, for instance. If the animation state machine called directly into the sound system and we try to multi-thread it, then we might get conflicts when different threads would try to use the sound system at the same time. Another thing here, which is also a general thing that we do in the engine, is that we tend to prefer polling over callbacks. So instead of getting callbacks from the animation state machine when the trigger is hit, which again leads to this problem with threading and context. On which thread do we get the callback? When in time do we get the callback? In what state is the animation state machine when we get the callback? What can we do from the callback? Can we touch every system? Or are there limits what we can do in the callback? And so on. Callbacks just create a lot of questions like that, which we avoid by polling, because then we know at what point we are polling the state machine, and we know exactly when we will process these events. So that's animation. I just say something short about AI too, because we don't have that much in the engine. We have very limited AI support in the engine because AI is very game dependent. It's not really, I think in general it's hard to do generic AI features because all games have very different needs for AI. It kind of depends on what the game is. But we have a few things that you can find in the engine if you look through it. We have a navigation mesh system, A-star pathfinding based on navigation meshes. But this system is kind of superseded by the navigation plugin that we have, that uses the Autodesk navigation system. So this isn't really that useful anymore. But you could use it if you need something simpler than the navigation plugin, or if you're fine with that. We have another AI system called the broad phase. That's a system for finding nearby objects. So if you want to, typically AIs will need to reason about the world, and they will need to know where to find health potions, ammo, stuff like that, cover points, whatever. This is sort of a generic system for that. You can enter objects into the system, like these objects are stored here, and then you can query the system to find what objects are near you. And this is based on grid hashing. So we divide the world up into a grid, and each grid cell is hashed into a lookup table for what we can find in this cell. So to find everything to find things around you, you sort of take the 4 or 9 closest grid cells to you and find all the things that are in those grid cells and look them up in these hash tables. But really, I think that all of these things that we have, the navigation mesh and this broad phase, really belongs in plugins. We made these things before we had the plugin system in the engine, and I don't think they should be a part of the engine core because they are not as general useful things. I think it would make more sense to have them as plugins, but they're there for now because they were created before we had the plugin system. One thing I would say about AI and animation is that there are lots of interesting problems to be solved that sort of happen in the intersection between AI and animation. Because currently, I think a lot of the time people are treating AI and animation as sort of separate issues because it's always easier to think about things separately. But they are quite close connected, because I think for animation to look really good, it needs a little bit of AI, because it needs to be aware of its environment. Typically, animation that looks really good does things like putting a hand on the wall when you get close to the wall, and just being aware of the environment in that way. And in the same way, I think that for AI to look good, it really needs good animation. If you have a really good path that the character follows, but the character just walks very stiffly along that path, it won't look like good AI. So I think there are things you could do, sort of connecting AI and animation. I think that's a sort of fruitful area to do stuff. That was all I had. Are there any questions that I haven't covered? All right, I think we'll skip the input talk today, because this was a really long one. We've already run over. So, oh, I see someone is typing. You can speak up too, if you want to. All right. Yeah. Yeah. Thank you. Thank you very much. We'll do the input talk on Monday instead. Cheers.
Bye-bye.